Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 45, we will talk about dimensionality reduction and feature extraction. So the different concepts that we will cover will be the basics about why we need to do dimensionality reduction and feature extraction. Then we will talk about principal component analysis, and then after that linear discriminant analysis, and we will then give two examples of PC and LDA in Python. So urban data sets are often very high dimensional. That means whenever we are trying to develop any form of models or we are trying to predict something, we actually use a lot of features to do those predictions. For example, socioeconomic variables, mobility patterns, land use characteristics, neighborhood characteristics, accessibility characteristics, and so on. So the number of variables that actually, when we have so many variables in a model and all, so we can say that, well, the data set is often very high dimensional. And many of these variables may be also correlated. That means it may not have, that means either of, when two variables are correlated, including both of them in the model doesn't make sense. Either you take one of them, or there must be some other way of, taking the effect of both of these variables into some third variable, right? So there may be redundancy also and noise, which all leads to difficulty in visualization and modeling. So because there is a lot of features, so obviously there will be some redundancy, there will be a lot of noise, and that leads to difficulty in visualizing the data set and also developing the models. So the primary goal is to reduce the number of dimensions that we are looking into, or to create a new sort of variable which represents many of these dimensions. So this is the crux of dimensionality. So with more dimension, what happens is, we have earlier learned several in different algorithms, we use the distance matrix as one of the measures to actually differentiate between the class boundaries, or to find the distance from the class boundaries and so on. So then that distance matrix loses its significance when we have got many dimensions. And the model complexity and overfitting risk also rises along with increasing amount of computation power. So that means that unnecessarily there is no point of increasing the number of features in a particular model. So dimensionality reduction actually does exactly the same thing. That is, it is a process of reducing the number of input variables while preserving the essential information. That means statistically we should not lose the information by deleting some of the features, or rather the model's explanatory power should not be reduced. And then two ways we can do that. One is feature selection. That means we should keep only the important variables. And the other way is to go for feature extraction. That means we create new variables, as we are discussing. So one of the ways to create new variable is the principal component analysis. It is an unsupervised method. That means we don't have any label at the end, and so based on the data set we can determine which features are more related to each other, and then we can combine them into new feature or create new variable. The other way to do that is to project the data into a lower dimensional space. This is known as discriminative projection. So one of the methods within that is linear discriminant analysis, and this is actually a supervised method. So using this we can also do classification as well. So it is not only a method to reduce the dimension, but also that can result in identification of classes as well. So this means projecting data into a lower dimensional space in such a way that different classes becomes more separable, and in most cases this is a supervised way of doing it. It's a supervised learning. Now then this is one way of looking into what to do about reducing features or extracting information from the features. So the other way to consider is both linear and non-linear dimensionality reduction techniques. That means most of the dimensionality reduction techniques of PCA or LDA all are mostly linear in nature. That means whenever we are looking into the different axes, eventually when we are doing projection, all we are taking a linear combination of features, right? But in many cases the data set is too complex, and then there should be the data lies in a curved manifold, right? So that means we require a non-linear techniques instead of linear techniques. So two of these techniques, which we will not cover in this lecture, but you can know about these two techniques, that is TSNE. It is a non-linear DR technique that preserves local similarity between the data points. And UMAP, it's again another non-linear DR technique that preserves both local and global data structures. So these two other techniques also exist, but these are mostly focused on non-linear features, and how that based on the nature of that particular data set. So coming to principal component analysis, PCA is an unsupervised dimensionality reduction technique that transforms correlated variables into a smaller set of uncorrelated components that capture maximum variance in the data. So that means we will try to reduce the number of correlated variables, or rather we should combine the correlated variables into a new variable, and then and we should do this in such a way so that we can capture the maximum variance in the data, right? So for example, let us see in the first figure where you see that we have plotted car ownership versus income. And usually it is understood that when income increases, the number of cars owned would also increase, right? So that means if I draw the scatter plot, you will find that it is all it's a scatter. It looks like a tilted, elongated ellipse, and with and all the points are in a diagonal direction, right? Now x1 and x2 are correlated, and both are giving mostly similar information, right? So in this case we are saying that if only I knew one, that would also be equally good. That means I don't require the information from two variables in this case, and that is resulting in redundancy. So so that means we are using 2 dimension, but actually the data is mostly 1 dimensional. So that means instead of 2, I can only focus on 1. So this is one way of feature reduction. Now what PCA does is PCA changes the coordinate system by rotating the XY axis, and it does so to align the main direction of the data cloud, and that means the data points are not shifted or changed, but the axis is shifted in such a way so that the spread of the data along that particular axis is maximum. So obviously in this particular case, instead of right now this is the axis is in in the way the axis is drawn. If I want to change the axis, right, so that means I have to do it in such a way so that it will align with my data. That means the data cloud. So when I do that, that means you will see that we will be able to draw it in such a way. That means we have to find that along those particular axes, the data variance, the data spread would be much larger, right? And if it is so, then we can identify in those direction where the spread is larger, and also the amount of that particular spread, that actually can help us in determining which features would be kept, right? Or rather, how to transform those particular features into this new direction. So PC1, that is principal component 1, or the first principal component, it is the direction where the data varies the most, right? And as per the figure that we have given earlier, it is the long axis of that ellipse that was drawn earlier. And the first component actually usually contains the maximum information about how much the data variability that can be explained, right? And the second component usually gives the next maximum variance information, and usually it is orthogonal to this particular first component, right? So in this case, of course, in case the data is along that in form of an ellipse, then the direction of the next largest variation is most likely to be the short axis of the ellipse, right? So the PC2 is basically PC1 and PC2 are actually the long axis and the short axis of the ellipse that we are earlier plotted. So the PCA algorithm, if I look into the steps that we have to undertake, so what it does is, that means we need to capture the direction of the spread as well as the amount of the spread. That actually will help us in identifying these different principal components. So the data, in the PCA algorithm, of course, the first stage is data collection. That means data set contains multiple quantitative variables that may be correlated. So that's why we are doing PCA. And this forms the high dimensional feature space that PCA reduces while preserving essential information. So the first job is to standardize. That means we are scaling and mean centering, right? So that means this ensures that if we have got variables or features of different types, and to ensure that all these variables are on a comparable scale, that's why we are doing this. So data is first mean centered and usually scaled to unit variance so that no single variable dominates, right? So that means x scaled is equal to x minus mu divided by sigma, where x is the original value of the feature, mu is the mean of that feature, and sigma is the standard deviation of that feature. And we get, after the scaling, then only we will start working with the data set. The next job is, of course, to create the covariance matrix. Now, the reason we calculate the covariance matrix, it is to capture the pairwise relationship among the scaled variables. So we have already learnt about this covariance, correlation, and all these things. So this tells us that how each of this pair varies together and reflects the internal structure of the spread of the data set. That means when two things are varying together, and also we are getting a figure of how much is that that particular variance, covariance, that can actually help us in the direction, understanding the direction in which this data is spread out. So high covariance indicates redundancy and correlation, and then we can, one approach is to choose only one of the factors, the other is to combine those into a new factor. So in this case, of course, we will do the second one, that is, we will combine them to find new factors. And the first we have, when we are we have to first calculate the covariance matrix, which is given, C is given as 1 divided by n minus 1, x is the standardized data matrix and xt is the transpose of matrix x, right? And why we divide by 1 minus n minus 1? Because it is understood as the unbiased normalization factor. So that means we are also normalizing this this dot product between the xt and x, right? So when we take this xt and x, this particular pairwise dot product between variables, then what we get is, in the diagonal axis we get the variances, and in the off diagonal elements are the covariances between the different features. Now the covariance matrix tells PCA where the data spreads the most, which direction has maximum variance, and how variants are aligned in spaces, right? So the next step is to go for eigenvalues and eigenvectors, and this is possible through eigen decomposition. So I'm not explaining the formula for this, but this is a standard way to extract the direction of the data spread as well as the amount of data variance along that particular direction. So eigenvalues and eigenvectors we have to compute. So it is done through the covariance matrix is then decomposed into eigenvalues and eigenvectors through eigen decomposition to identify the direction of maximum data variability, and eigenvector is the direction of the data spread after transformation, whereas eigenvalue is the amount of variance along that particular direction. Now eigen decomposition is given by CV equal to lambda v, where lambda is the eigenvalue and v is the eigenvector. So this is the principal direction, and this is the amount of variance that is being explained. Now eigenvectors are special vectors where the output vector is in the same direction as v, but its length changes only scale. So we are doing only scaling, there is no rotation here, right? So what we have to do after this is, once you have identified the direction as well as the spread of this particular spread of this and this spread, then we will sort these eigenvalues in descending order. Now the reason is, when we are sorting the eigenvalues in descending order, we are capturing the larger eigens, we are trying to find out which are the larger eigenvalues, right? So components with larger eigenvalues, we understand that they capture more variance. So obviously those are identified as the principal directions, right? So these are arranged in descending order to rank the principal component based on their importance, and this helps determine which component should be retained in the dimensionality reduction. So as you can see, we have arranged the eigenvalues in descending order, lambda 1, lambda 2, lambda 3, and for each of this we also have got V1, V2, which is the PC1 direction, and PC2 direction. So what we do is we take the next step is to select the top k principal components. And how do I do that? I take a summation, we choose the smallest value of k such that for summation I equal to 1 to k, lambda I divided by sum of lambda j, so which should be lesser than equal to 90% or 95%, right? So what it means, this is the total value that is given, and then this is the variance that is explained by only the the first one, and then we take a cumulative of it, right? So that means we are for the value of k, where we after adding on this particular these variances, we are achieving around 90 to 90% variance can be explained, then we can say that that is the right value of k, or so many principal components will be chosen, right? So a subset of top k principal components is selected based on cumulative explained variance criterion, which usually is 90 to 95%, and this ensures that most of the original data variability is preserved while dimensionality is reduced. Now the next job is, of course, now that we have identified the principal directions along which we should identify, so next job is to transform the data into this reduced dimensional spaces, into this along these two principal components, right? So the standardized data set is projected onto the selected principal components to obtain the reduced feature representation. And what it does is this converts the original correlated variables into a smaller set of uncorrelated components, and which could be used for further analysis, right, for building models and so on. Now the projection matrix Vk will include all the different values, all the different PC directions, the principal components V1, V2, Vk, and so on. Now we compute the principal component Z equal to x into Vk. That is the the number, the top k that we will take. And so in this particular case, suppose there are only two principal components. In this case, PC1 would be x into V1 and PC2 would be x into V2. So larger is the eigenvalue, is more important is that particular component. Now the next job is to find out what are the values of V1. Now each eigenvector or each principal component is, which is V1 is, these are the principal components. Each principal component is a linear combination of original standardized variables weighted by eigenvector loadings, enabling interpretation of latent urban factors, right? So that means what we are doing is each of these eigenvectors V1, because we are dealing with multiple features, right? So this will have, it's a linear combination of the original standardized variables weighted by the eigenvector loadings, right? And because we have done this covariance matrix and we have extracted after eigen transformation, we have extracted the eigenvectors. So V1 will be something like this, where you see the different it's an indicator of the strength of the different features, right, in that particular direction, the new strength of features. So these are also known as component loadings. Now PC1 would be computed like this: 0.7 x1 plus 0.6 x2 plus 0.1 x3 and 0.5 x4, where variable 1 has got strong influence, variable 2 has got strong influence, variable 3 and variable 4 have got weak and very weak influence. So this is the component loading, and this is the final factor score that we are getting for PC1. Now next comes so that is how we do PCA. Now coming to linear discriminant analysis, as we have learned earlier, it is also a dimensionality reduction technique, but here the approach is different, and it is also unsupervised as well. So it's not unsupervised like PCA. Now what we do over here is that the dimensionality reduction is done by projecting the data into a lower dimensional space while maximizing class separability. So the idea is we are trying to project the data in a lower dimensional space so that the separation between the classes is large. So PCA, what it does is it finds the direction of the maximum data variance. But LDA, it looks in a different way. It tries to find a direction where it will maximize the separation between the predefined classes. And that is also one goal we have learned earlier also when we have done clustering and all. We try to separate the classes as much as possible. So in PCA, we have done the we have taken the covariance matrix, and then we have tried to find the eigenvalues and eigenvector. We did the eigen decomposition. But in LDA, what we do is the direction or the spread that is determined by this particular the within class scatter matrix and between class scatter matrix. So that means between class scatter matrix is talking about distance between the class means, right? So that means when I have decided on these are the clusters for each of these classes, that means we will take the mean, and the distance between them, that has to be maximized. And within class scatter matrix means the spread of the samples within each class. In this case, the more clustered are those values, it is better, right? So more near together. So in this case, we will try to reduce it as possible. So accordingly, SW goes below, so that is -1, and SB is above, right? So that means it is we are taking SB divided by SW in that way. So what are these SW and SV? So SV, already we have discussed that this one is the spread of samples within class and the other is the distance between class means. But because it's a high dimensional data, we have to again look it in a way so that we can measure the different values properly. And so SW is measured as for suppose we assume there is C number of classes for I equal to C, and then DI is the data set, that means the overall value, and X is a data point in class I, and mu I is the mean centroid of that particular class I, then X minus mu I is the distance of a point from its class center. So we first determine this for each of these classes. For each of the values of variables in those classes, we determine its distance from mu I and then also multiply that with its transpose. So once we have done that, we take a summation of those values, and then we get SW. Similarly, for SW and for SB, what we do is we take the number of samples in class I, and the mean vector of class I is also determined, and the mu is the overall mean of all data points, and we actually use the distance between the mean vector of class I and the overall mean of all data. So we are trying to take that value, and then this distance of class mean from global mean is computed, and once we have done that, then we take transpose of it, and then we again take summation for each of the different classes, and then we get the value of SB. So larger SB means classes are well separated, smaller SB means classes overlap. So once you see that, we are trying to maximize, the point is that we should maximize the distance between the classes, and the distance within the classes should be, the scattered within the classes should be minimized. So that is what LDA optimization objective is. That is, LDA finds the projection matrix W star that maximizes separation between classes while minimizing spread within each class. So you see that W star is equal to the it's the optimal projection direction in the LDA axis, and then we take and SB is the between class scatter matrix, and SW is within class scatter matrix, and we take determinants of that. That means we take the determinants of this so that we get, that means a single value. So we get an overall scatter magnitude, a single value from this particular matrix, and it's and because it is already calculated based on the distances and its transpose, so automatically we will able to get a single value which is being done, and argmax finds the value of W that maximizes the ratio. So once we have done that, we have to also make sure that the maximum LDA component should be lesser than equal to C minus 1, where C is the number of classes. So that is that should be there, and it cannot be more than so it cannot be more than that. And then the LDA algorithm actually has to start, first of all, the data has to be labeled, and we have to have that data set ready. Then we will compute the mean vectors, class mean vectors, to identify the centroid center of every class cluster that we are starting with. then we compute the scatter matrices XW and SB, and then we solve this SW to the power minus 1 into SB into V equal, and this is the direction we are trying to find. That is, we find the optimal projection direction that maximizes the class discrimination, and finally we project the data onto this particular new discriminant axis, and this transformation of the original data happens when we do this projection, and what we do is, once it is done, then transformation of this original data onto the selected discriminant vectors is done to obtain the lower dimensional space with maximum class separability. So once we do that, then automatically you will see that the approach is a little bit different from this PCA, but eventually we are also trying to find the directions of in the directions where we should project the data, so that in this case the classes are mostly separated. Now coming to the example in Python, so the first problem, what an urban planner is willing to identify the hidden patterns linking built density, heat, reflectivity and air pollution, and classify areas by the overall environmental stress level. So that means in this case we have data set which is talking about the impervious surface percentage, building density of those areas, units per hectare, then the land surface temperature in Celsius, the albedo index and the PM 2.5 levels. Now we are trying to find out that are some of these factors are correlated, or is there a need for considering all the factors, or we can take only a couple, we can also combine them into something alternative, different latent factors, or to replace those individual features, right? So to do this, of course, we have to run PCA in this particular case, and to do PCA we will import the standard libraries, that is Panda as PD, NumPy as NP, then from sklearn we are importing standard scaler so that scaling could be done. Then from sklearn we are importing PCA so that we can run PCA over in this program, and then we are importing matplotlib and also the Seaborn, both for plotting requirements. So first we import the data set and we store it in data pd.read_csv. So this is the file which is being read and stored in the data frame, and then so then we are storing it in the data frame over here, and once it is done, then we can run the standard scalar function to scale the data, and then we are storing that in, after we are running it, then we are storing it in x_scaled. So this is the data set that we are going to work with. So the next job is we can check the multicollinearity to see the correlation matrix, and for that we can say df.core, which will give you the correlation matrix, and we can print it. And as you can see over here, there is a lot of correlation between the data, and these values are pretty high, and that means we need to do PCA, and PCA is statistically justified. So that means because there is a lot of high correlation, we can go for PCA to reduce the number of dimensions. So we will then run the PCA, and we store the value in this PCA again, and x_PCA will have the results, and so PCA.fit_transform. So we are fitting the data x_scale, that's the data after scaling, and we are first fitting our this into the PCA program, and what we can do is, once it is we have already done the measurements, then we can explain we can check the variances that has been explained. So PCA.explain_variance_ratio tells us that what proportion of the variance has been explained by the different the PCAs, right, different principal components. So for I, where in enumerator explain variance, print f quotes PC I plus 1, and this actually what it does is it will help us to identify the total, first of all we are printing the values of these variances that are explained for each of the principal components, that is over here, and then we can see that most of the variance is explained by PC1, but we can always take another one which is PC2, and together they explain around 93% of the variance, which is between 90 to 95%. So we will decide that we will retain two components, right? So we can also draw a scree plot, not required, but we can draw it as well. And over here we have used we have drawn the scree plot over here. So what we have done is we have taken the cumulative based on the number of components. We have taken the cumulative explained variance. So that is what we are that is what we are taking, the np.cum SUM explained variance. So this actually takes the cumulative value, and then we are plotting it over here, and you can see that there is after PC1 after the we start from 0.88. Actually, if it was done from the beginning, it would look a little bit different, but to simplify, we have started with 0.88, and after that we are seeing that there is a turn. That means there is a sharp drop after PC1. Elbow at PC2 confirms a two-component solution. It's not that clear, but yes, so there is a turn, so that we can say that a two-component solution is better, because the amount of explained variance is not increasing that much after this PC2. So after two components, right? So once we have done that, then we fix our PCA for two components, and then we can determine the component loadings and the PCA scores or the factor scores, right? So the first job is we are trying to find the PCA component loading, so that we get from PCA.components_.t, and then what we are doing is we are again storing this data in the columns, and what you can for using a for loop over here, and then we are also printing this and printing this loadings, which is storing this entire data set. So over here you can see the result. So for each of the so you can see PC1, PC2, PC3, PC4, PC5. So out of that we have decided only to go with PC1 and PC2, and so these are the individual, when you take PC1, you break the V1 value. So these are in each, this for every feature, this is the factor that that is the score, the component loading that will come, and once the component loading comes from PC1, PC2 and so on, we can compute the factor scores. So we take the scores for the first two components, and that is done over here, x_PCA and colon comma colon 2. That means the first two principal components are being taken, and we name these columns as PC1 score and PC2 score, and then we are combining it with the original data, and we can print the entire thing by concatenating, and then we can print the scores, just df_PCA scores actually print the entire thing. So over here you can see for each of the variables we can print the PC1 score and PC2 score, and you get, this is the based on the component loadings, this is the values we are getting. So the first few ones shows high positive PC1 scores, and the low, and this one shows strong negative PC1 scores. So this actually tells us that in case of regression or some other models that you want to build, so I can introduce a new PC1 component with this particular score for this particular row of data, and this could be utilized in the regression equation. Instead of all the data, all the different features, we can go for only PC1 and PC2, and that would be able to explain the detailed variance, most of the variance for this particular data set. Now coming to LDA, example of LDA in Python. So in this case, what we are doing is we are taking a categorical target variable. So that means we want to find the direction that best separate the classes. But for this data set, what we are doing is for each area there is density, traffic, heat, noise, pollution, green cover, and so this data is there with us, and at the end of that we also have the class output, which is the class level or either residential, commercial and so on. So basically this is the character of that particular area, and then we have, this is the the land use of that particular area, the primary land use, and these are the characteristics like density, traffic volume. These are the different features of that data set. So we are trying to do LDA to identify combinations of variables that best distinguish between these zone types, right? So the zone types are residential, commercial, industrial and so on. So that means which features are contributing more to identify these zones to be of separate kind, right? So that means we can build a model to predict the type of zone based on which of the features, right? So that is our goal. So again we import pandas, numpy, these are standard, then matplotlib, cbron, same as the previous problem. Then sklearn, we are importing test trend split because we will run, it's sort of it's a regression model, so we have to test and we have to keep some data for training and then for testing, and then we import standard scalar, then we import linear discriminant analysis from sklearn, right? And from sklearn.metrics import accuracy score classification report. So this is also because we are doing you are predicting classes, we are also using accuracy score classification reports to find out how good is our prediction. So then we import the data set, we read the data set from ida_zones.csv and we store it in this data frame df, and then first we will determine what are the x and the y values, that is what are the explanatory variables and what is being predicted. So y is definitely the zone type, so df zone type is the y value, that is what is being predicted, and then the different all the other columns except for zone id and zone type are, because zone id is just the number of that zone, it's not a feature as such, and the zone type is already the y variable. So in that case the other variables would be taken as x. The next job is to train, test, split, do the splitting of the data, and we have taken the split as 0.3, the test size as 0.3 and random state 42, and and that is how we are starting, first dividing the data into two parts and then we are starting to build the model. So we first scale the data and using standard scalar, and so both x train as well as x test is both transformed, right, after after using the standard scalar. And then finally we call the linear discriminant analysis and function, and where we set the total number of components to be 2. That means there will be two directions or two dimensions of projections, right? So then x underscore train IDA, we will fit this particular LDA model. So LDA dot fit underscore transform, and we are putting x train scaled and y train as the input to it, right? And then once we have done, then x test underscore IDA is equal to IDA dot transform x test scale. That is, this is the train data, and then for test data we are also running running this linear discriminant analysis to do the prediction. So y predict equal to LDA dot predict x test scale. So that means we are first putting the data this x test scale, and we are using this data to do the prediction, right? So once we have done the prediction, then obviously we can calculate the accuracy scores, and the we can print the accuracy scores, classification report, confusion matrix, and so on. So over here you can see accuracy value is 0.8. So out of 5 test zones, the model correctly predicts 4 zones. The classification report is given. We already know how to read a classification report. The confusion matrix is given over here. So what it says is the one commercial zone in the test set, this is predicted correctly as commercial. 2 industrial zones in the test set, both predicted correctly, and 2 residential zones in the test set, 1 predicted correctly and 1 misclassified as commercial. So this is the situation, and then then what we are doing is we are plotting the LDA components in a figure. So what we can do is we are plotting both the different the class along the LDA1 and LDA2 two directions. We are plotting that the projected data, and what we are seeing is we are also giving different colors for the different classes, and we are getting this commercial in blue, industrial in saffron, and residential in green. And then we are doing this scatter plot for this ytrain dot for label in ytrain dot unique. We are plotting it the values, and then we are getting this plot where you can very easily see that this is the classes being predicted which is separated, and as per LD we have already known that the more is the separation is the better. So accordingly along this LD1 and LD2 it is proper, the data gets properly separated so that classes can be predicted. So these are some of the references that we have used. To conclude, PCA reduces redundancy by capturing maximum variance in correlated urban indicators, whereas LDA enhances classification by projecting data into a space of maximum class separability, making both essential tools for intelligent urban data analytics. Thank you.